All right, Dr. Mr. Swartz, Jet Energy.
Hi. To me, cold fusion's been like the Louisiana Purchase. We have entered a new realm. We found new materials. We found new ways to drive them. And what I thought I would do today was go through some of the things that we found that have led to possible products.
All right, from the top.
Okay. We all know we need cold fusion because fossil fuel has penalties for using it, so we must get rid of it. The reason I like cold fusion is in our latest nanor that we were running over at MIT, we can see here plotted out is energy density and power density for supercapacitors, batteries, yada yada. And over here's the nanor. And to me, that is what has been keeping us going. We have a source that can replace fossil fuel. And who are we at Jet Energy? Well, we've been hiding out here. We've just moved to here in a city. And in fact, here is now too small, so we're ready to go to a second building. What we have are a number of products. We have the aqueous fusor that we showed in open demonstration at MIT in 2003. We have the nanor that was shown at MIT for 5 months in 2012. And probably Alan Weinberg should have given this talk. He's much better than me, talking about the company. And we've worked with a lot of people to get this done, especially the nanomaterials. And so I really want to thank a lot of people, and their names are up here. And because we only got 15 minutes, I'm going to move ahead a little bit and let you photograph it. Our goal at Jet Energy is to figure out how to make cold fusion through nanors available to everybody as a platform so that you can get power gain and use it in a circuit, use it for an artificial internal organ, whatever you want to use it for. We've had a number of milestones to date. Though we were quiet about it at the beginning, we used co-deposition since '89. It did not give very much excess energy. We discovered optimal operating point operation, which a lot of people still are not using. It helped us develop the fusor, which at MIT, at the 2-watt level of excess power, ran at a power gain of 2.7 for 5 days. After that, by the way, the quasi-one-dimensional model was in fusion technology. I really recommend you look it up. The Navier-Stokes equation is the way to do cold fusion. And what it is that successful cold fusion is not electrolysis. It's 1 minus electrolysis. And although our posters were put in the gas section, we don't gas load them. We do it through electrolysis and then we drive. Anyway, through the quasi-one-dimensional model, we got co-deposition, optimal operating points. It's been an incredibly successful theory. We got control of tardif thermal power. That led to we were using Stirling engines. We can show some of that tomorrow. And we've had successful, these are co-deposition, this is a dual anode fusor. And then finally we led up to the nanor that we showed at MIT, which is a dry, preloaded material. It looks like a 1-watt resistor. It has 2 leads. You put a current into it, a DC current, and you get up more than V times I. So for me, that's a very convenient way to do things. We have tried to file for a lot of IP. The patent office always says there's no utility to cold fusion. We send them the data. We send them the pictures of people coming to MIT, including the Senator Tarr from Massachusetts, and they go, there's no possible utility. Now, what we have used in the development of our systems is evidence only obtained with multiple verified calorimetry. So when we do calorimetry, we'll do delta T measurements, heat flow measurements. I'll use as many as I can together, and that gives us credence to move on. So for example, at MIT, we show that I'm having the same trouble everybody did here, sorry about that. We put an ohmic control here next in, with the thermocouple in between, the nanors on the other side. This is filled with a large thermal mass. We also measure the heat going out. And that led us to be able to have 3 independent ways of measuring the instantaneous power gain. And then by time integration, we're able to get the energy gain and then rule out false. We also do noise measurement to rule out false positives. It's too long to go into it now. In addition to parallel measurements, we do serial measurements for calorimetry. So for example, with the Stirling engines, we'll look at delta T at the source, we'll look at heat flow moving out, we do dual control, we'll actually, in addition to having dual paired Stirling engines, we'll do delta T measurements on them as well. So we use both parallel and serial calorimetry to make sure we know what we're doing. So here's some of our technical achievements that we showed back in 2003. Here, what we're looking at is time. This is in minutes. This is power in watts. So it goes to 4 watts. This is the integral of this, so we're up to joules by integrating the power over time. Here we see the input power to a control. I always use ohmic controls, and we get a nice match out. We put it into the fusor. This is an aqueous system. It is a high impedance, heavy water solution with no added salts. The fusor is a metamaterial. That means that its properties are beyond normal material properties, composition. Its shape plays a role. That's what we mean by metamaterial. And here you see a gain of about 2.7. So we did a demo at MIT. Everybody came. Popular Mechanics was interested. They put this in there. Here you can see that this went over several days while this, well, let's do that again. While this is being done, here's the control, another control, another control. And at the end, we get quite a significant energy gain. So here's our energy gain. These are our power gains, and the power gains are right off the left. Okay, well, it turned out by using the same system, we also got excess energy from ordinary water with nickel. And here, for example, you see a nickel cathode, and this one, I believe, had a platinum anode, and here was I have it the other way. This is with the gold anode, this is with the platinum anode, but it's essentially the same. We do a noise measurement. Here's the ohmic control input, here's the output. We get a little bit less out than we put in, and yet, this is on a log plot. Here, when we put it into the fusor, we get more out than we put in. So we have clear demonstrations of excess energy gain over time. We invited many people to see it. This actually ran, we did this at MIT. I think it was October. We had multiple people coming, so it ran over a year. Then by 2004, we were using paired systems where we had Stirling engines like mentioned this morning, but we use a control. I always use a control. So we'll have an identical calorimeter with a ohmic resistor inside. And in this case, this one didn't even move, and this one went whatever miles it was. And it was a very impressive way to show a differential of input to a resistor versus a cold fusion device, so we get more out. Now here's the nanor. Now the nanor is a dry material, as we'll talk about tomorrow, made of zirconium oxide, and in it is put palladium. Think of it like a chocolate chip cookie. The cookie is zirconium oxide. It's highly electrically insulating, and the chips are PDD that we end up loading. So let's look at the results. Here we see the time. I apologize. This is each count here is 7 seconds. While we were running it, anyway, it doesn't matter. Here we see the ohmic control. All of these are going to be the same. We do a control pulse to calibrate our measurement equipment. Then we do an ohmic control to calibrate the calorimeter. And then we do a series of inputs to the nanor. This is the cold fusion device. And here for this series 5 nanor, this ratio is the instantaneous power gain at each of these power levels. Okay, so it's a clear demonstration of excess energy. I hope I got enough time. In fact, let me jump ahead. We showed it at MIT. This was the one during the course where we ended up here. This is looking at delta T versus input power. So here's our time in seconds. Here's the control pulse calibrating the equipment. Here's the control itself to calibrate the experiment. Here's the input to the nanor. So we can see that for less input, we're getting a higher delta T. And one of the things we do is we'll divide delta T by the input power, because that will take that last line that rises and make it flat. And by doing that, this ratio, if you do delta T divided by input power, you can get the instantaneous power gain quite quickly. Here's the calorimetry. What I'll show you tomorrow is we have new devices called M-nanors, which have incredibly high gain. Look at this. Here's our ohmic control. Here's the cold fusion input, and here's our output. Massive gain. And in fact, you can see that, in fact, in terms of the energy here. Here's the energy put into the nanor, and here's what we get out. Sweet gain. As a result of it, Jet Energy, we launched a new company July 1st called Nanortech, and the plan is to focus solely on using these nanor-type devices, dry devices. We're going to make it a little bigger than we showed at MIT. We built it at MIT to run at the 1 watt level, well, the 10th watt, half watt level, because we were concerned mainly about safety. We were going to try and let it run as long as we can, and to let it run over the weekend and overnight, where we're not there all the time. I just wanted safety for reasons we can talk about later. Anyway, Nanortech will solely be involved with creating an awareness and experience of this new technology and trying to make the nanor available. And here's where we're going to try and put it. Our first goal is academic and educational institutions. Then we're going to use the platform for these other things that you can read. This is what Alan calls our segment funnel. And I think someone in marketing can explain this better than me. I'm just a scientist.
Thank you for getting all those slides in the allotted time. That was terrific. Please give it up for Dr. Mitchell Swartz.